Sir, good morning, sir. Ravi, sir. Sir, your voice is not audible, sir. Can you please unmute, sir?
Okay.
Yes, sir. Good morning, sir.
Good morning.
Just a minute, sir. We will start the session.
Okay.
Thank you, sir.
మన పేరు కనపడదు మన కనబడి వాళ్ళ కనబడుతుంది పేరు ఓకే ఓకే థ్యాంక్ యూ డోరెస్
A warm morning to all the participants, guests, and research scholars. Myself, Dr. V. Lakshmi Devi, Professor in Triple Department, welcome you all for AST sponsored Sorry, we are facing some technical issues. I'm recalling again. A warm morning to all the participants, guests, and research scholars. Myself, Dr. V. Lakshmi Devi, Professor in Triple Department. Welcome you all for the AST-sponsored STTP Phase 3, Recent Trends in Renewable Photovoltaic Systems and its Research Challenges. Welcome for the Day 2. Today we have two sessions. For the morning session, we have Dr. Ravi Kumar, sir. And for the afternoon session, we have Srinivas sir. They are going to discuss on the recent trends on the topics. Ravi Kumar sir is going to discuss on application of fractional order controllers to power systems, and whereas Srinivas sir is going to discuss on introduction to smart grid. Now I request Vaishnavi to address the gathering. Vaishnavi?
Yes, ma'am.
Yes, please
Okay,
start the session.
Yes, ma'am. Thank you. A very good morning to one and all present here, and a warm welcome and a fresh morning to everyone gathered here. As ma'am said, it is the second day of training program. Hope the first day is very successful, and also I ensure the training will be more profitable. As sponsored by AICTE, 1 week short-term training program on research trends in renewable photovoltaic system and its research challenges phase 3. So before going to start the session, some instructions as the participants are requested to mute your microphones and turn off your cameras, and also suggested to pin the resource person screen. And now I consider it a great honor to welcome our resource person this morning, Dr. C.H. Ravikumar, presenting on application of fractional order controllers to power systems. Sir is presently working as assistant professor in the Department of Triple at Acharya Nagarjuna University. He completed his BTech at JNTU Kakinada and did his MTech at JNTU Anandapur, and also awarded PhD at Acharya Nagarjuna University. Sir has published 10 international journals and attended 2 IEEE international conferences. He also awarded Best Paper in International Journal category and secured second place in IEEE International Conference conducted at Malaysia in 2015. So now I request Dr. C.H. Ravikumar sir to take up the session. Sir, welcome, sir.
Thank you, Vaishnavi. And thank you, Professor Lakshmi Devi for introducing me.
Thank you,
Okay.
sir. Thank you.
Is my voice audible, ma'am?
Yes, sir. It was clear, sir.
Okay. Now I will start the presentation. Good morning, all the participants.
Sir, can you please present the screen, sir?
Yeah. Is my screen visible, ma'am?
Visible, sir.
Are you getting the screen?
No, sir.
No?
Can you represent, sir?
Yes, ma'am?
Yes, sir. Now it's visible, sir.
Okay. Thank you.
Yes, sir. Now it's visible, sir.
Thank you, ma'am.
Thank you.
So I'm going to give an expert talk on intelligent and fraction order based load frequency controller for multi-area power systems. Okay, so I hope everybody know about the load frequency control problem. Okay, so these are the contents which I want to present about the load frequency controller and different types of controllers to control the frequency deviation. Okay, so my concentration is fraction order controllers and the optimization of fraction order PID controller parameters by using particle swarm optimization, quad swarm optimization. Okay, so first I will introduce about the problem. Automatic generation control or load frequency control is very important in power system operation and control for supplying sufficient and reliable electrical power with good quality. The successful operation of interconnection system requires interconnected power system requires the matching of total generation with the load and associated system loss. As the demand deviates from its normal value, with an unpredictable small amount, the operating point of the power system changes. As the operating point of the power system changes, which causes the system experience a deviation in the system frequency and tie-in power exchanges in their scheduled values. Kabatti, the main objective of the automatic generation control is to keep the frequency deviation as well as the tie-in power exchanges in the scheduled value by performing some suitable control action. Okay, so this is the simple two-area interconnected system. Okay, so area 1 and area 2 are interconnected with tie lines. Okay, so the main objective of the automatic generation control is to keep the suppose manaki demand kanaka ekkuvaindi anukondi, there is sudden change in load. So as the operating point of the power system changes as the demand increases. Okay, so at the operating point of the power system changes, there is a deviation in the frequency as well as the tie-in power exchanges. Okay, the main objective of the load frequency control is to keep the frequency deviation in area 1 and area 2. Okay, and also tie-in power exchanges between the area 1 and area 2 and the scheduled values. Okay, so here area control error, you can observe area control error, which is the linear combination of the frequency deviation and Thailand power exchanges. Okay, to keep the frequency deviation and Thailand power exchanges in the scheduled values, drive the area control error to 0 by performing suitable control action. Okay, there are different types of controllers. Researchers suggested so many controllers. Okay, so among that, we will discuss some conventional controllers and intelligent controllers, and mainly fraction order controllers. So this interconnected system mainly consists of two loops: primary control loop and the supplementary control loop. Okay, primary control loop controls the frequency by self-regulating feature of the governor. Okay, so the governor has self-regulating feature. Okay, so by using the self-regulating feature, it controls the frequency. But whereas supplementary control loop, okay, it can entirely eliminate the frequency error. Complete error can be eliminated by using the supplementary control loop. Okay, so the main objective of the supplementary control is it restores the balance between the load and the generation after the load perturbation. Whenever the load deviates from the nominal value, okay, the supplementary controller it balances the load and the generation, load and losses with the generation, so that the frequency and Thailand power flows can be maintained at the scheduled values. So the main objective of this load frequency control problem is, okay, eliminate the frequency deviation and maintain the Thailand power exchanges at the scheduled values. Okay, so these are the different types of controllers which we will be discussed. Conventional controllers, optimal controllers, intelligent controllers, and the fraction order controllers. Okay, so I hope you already know that the conventional controllers for this automatic generation controller, load frequency controller is very simple to implement, and conventional controller also gives good performance. But the only problem with the conventional controller is, as the system becomes complex or non-linear, conventional controllers will not work well, or the performance is low in case of if the system is non-linear or the complex. Okay, and coming to the optimal controller, so optimal controller ante number of state feedback controllers based on linear optimal control theory have been implemented to achieve the better performance. So optimal control means we are going to design the controller with the fixed gains. We are going to design the controller with a fixed gains. But because of the inherent characteristics of the power system, the operating conditions changes. As the load changes, the operating condition of the power system also changes. These fixed gain controllers may not work well, may not perform well for the wide range of operating conditions. Only these fixed gain controllers works well for the nominal operating conditions only. That's why these conventional controllers and optimal controllers does not work well as the system become complex, or if you operate your power system over a wide range of operating conditions. Okay, so the above problems can be overcome with the use of the intelligent controller. Okay, intelligent controllers means fuzzy logic and artificial neural networks. Okay, the advent of intelligent control techniques has solved the above problems to a great extent. Okay, the main feature of these techniques is that from the traditional control approaches is they provide a model-free description of the control system. Okay, intelligent controller, no need of the mathematical model. Okay, for the description of the control system. Okay, so artificial intelligent controllers like fuzzy and neural controller approaches are more suitable in this respect. Okay, so in this here I am explaining about the fuzzy integral controller. I don't want to explain the steps to design the fuzzy controller. Okay, so these are the 4 stages involved to design the fuzzy controller, fuzzification, knowledge base, inference engine, and defuzzification. So these are the 4 stages in the fuzzy controller. So in the proposed controller, in the proposed intelligent controller, the input for the fuzzy logic controller is, I consider area control error is the input. Area control error is the input. Already మీకు proposed system present చేసినప్పుడు we define the area control error, which is the linear combination of the frequency deviation on the tail and power exchanges. Okay, that area controller error is considered as one of the input for the fuzzy logic controller. And the derivative of the area control error is another input for the fuzzy logic controller, and the control output is the output of the fuzzy logic controller.
Ravi sir, hello. Hello, Ravi sir. Kindly request all the participants to be on the line. We'll check. We'll sort out the issue. Ravi sir was facing some technical issues. Please cooperate. Sir is going to join through mobile. So just for 2 minutes, please kindly consider.
Ravi sir? Yes, sir. Yes.
Okay, small technical problem. Is my
Yes, sir.
screen visible?
Yes, sir. Okay, it's visible, sir.
Okay. So here, for the load frequency control problem, I implemented intelligent controllers, integer order PID controllers, and adapt neuro fuzzy inference system, and also fraction order PID controllers. Present, I am explaining about the intelligent controllers. So in the intelligent controllers, we developed uh, fuzzy controller. So for the fuzzy controller, the inputs are area control error and derivative of area control error are taken as the inputs. So these are the membership functions, triangular membership function with 7 linguistic variables: negative big, negative medium, small, zero, positive small, positive medium, and positive big. Okay, so this is the rule based for the implemented fuzzy integral controller. Here I add integral controller for the fuzzy also to eliminate the steady state error very quickly. And this is the adaptive neuro fuzzy inference system. Later I will show the outputs, how the frequency deviation and Thailand powers are eliminated with the use of the fuzzy integral controller and the adaptive neuro fuzzy inference system. Okay, so this ANFIS, it is the combination of the neural networks and the fuzzy logic. So here it needs some training data. The training data can be obtained from the input-output pairs of the fuzzy integral controller. So previously I explained fuzzy integral controller. Okay, the fuzzy integral controller is used to provide the required training data. Required training data can be obtained from the fuzzy integral controller. So the controller design process consists of generating input-output data pairs to identify the control variables range, and fuzzy membership functions, and then to tune or adapt them using the ANFIS network. Okay, the controller inputs are area control error and the rate of change of area control error. For ANFIS also, the inputs are area control error and the derivative of the area control error, and the output is the control signal. So these are the design steps to design the hybrid neurofuzzy controller. Okay, first simulate the fuzzy integral control. Later collect the training data while simulating the fuzzy integral controller. Okay, the training data constitutes 2 inputs and 1 output. 2 inputs are area control error and the derivative of the area control error. Okay, all these are considered as the training data. This training data gives as much information as possible about the behavior of the plant for different load changes. Okay, these input-output data pairs can be used as the training data to design the hybrid neurofuzzy controller. To design the ANFIS controller, we need the training data, and the training data can be obtained from the fuzzy integral controller. Use ANFIS edit to create the .fis file. Okay, load the training data collected in step 2. Step 2 lo collect చేసిన training data ni load చేస్తాము while creating the ANFIS adaptive neurofuzzy inference system, and generate the FIS with the suitable membership functions that may be Gaussian or GWell. Okay, train the generated FIS file after loading the training data. Okay, train the generated FIS file with the collected data up to certain number of epochs. In this study, ANFIS is trained with back propagation algorithm using 10 epochs and step load 10 epochs and step load variations are 1%. So in this work, I consider the 3 area interconnected power system: area 1, area 2, and area 3. Area 2 is in middle. Area 2 is connected to area 1 and area 3. Okay, whenever there is a change in load from the nominal value, there is a deviation in the frequencies delta F1, delta F2, and delta F3, and also there is a deviation in the tile and power changes from area 1 to area 2, delta P12, and area 2 to area 3, delta P23. So whenever there is a load variations from the normal load variation with an unpredictable small amount, the operating point of the power system changes, and there is a frequency deviation and tile and power exchange. Okay, the main objective of this load frequency control is to keep the frequency deviation and tile and power exchange in the scheduled values by performing suitable control action. Here we use the fuzzy proportional integral controller or ANFIS controllers, okay, to eliminate the frequency deviation and the tile and power exchanges and the scheduled values. So these are the output waveforms for the fuzzy integral controller for 1% step load variations. Okay. The first diagram shows frequency deviations in the area 1, area 2, and area 3. I consider the load variation in area 2. I consider load variation in area 2, which is connected to area 1 and area 3. Okay, Kabati, you can observe the frequency deviation, green color frequency deviation in area 2. And these are the tile and power exchanges, red color, delta P12 and delta P23. Okay, as time becomes 15 seconds, almost the frequency deviation is eliminated. Deviation in the frequency is eliminated at the time of 15 seconds. But whereas coming to the tile and power exchanges, okay, it settles at near 30 seconds. Tile and power exchanges. Next, the same fuzzy integral controller for 10% step load variation. Again, I consider the load variation in area 2. Okay, red color, area 2. Okay, you can observe the peak overshoots and the settling time. Okay, almost 25 seconds, 20 to 25 seconds it takes to eliminate the frequency deviation as well as the to get the scheduled tile and power exchanges. And so these are the simulation results for the adaptive neurofuzzy inference system for 1% step load variation. Here also exactly at 15 seconds, okay, we eliminate the frequency deviations and tile and power exchanges also, deviation in the tile and power exchanges also eliminated at 15 seconds. As already discussed, this ANFIS controller also works well as for wide range of parameter variations also. I also consider the variations in the parameter. Why? Because throughout the operation, the parameters of the system may not be constant. That's why I consider up to plus or minus 50% variation in the parameter. Parameters like speed governor constant, time constant, and turbine time constant. These are the parameters which varied from plus or minus 50% parameter variations. Okay, this ANFIS control also works well for the wide range of parameter variations. This is for minus 50% parameter variations. So that's it about the intelligent controllers like fuzzy integral controller and the adaptive neurofuzzy inference system. Now coming to our topic, okay, fractional order PID controller. Before going to discuss about the fractional order PID controller, so this is the structure of the PID controller. This is the structure of the PID controller. The classical PID controller is most widely used controller for industrial applications due to its simplicity in realization and tuning. Okay, So you can easily construct the integer order PID controller, and you can easily design the PID controller for industrial applications. Okay, so but in the recent years, the researchers introduced the concept of the fractional order controllers. Okay, here in the fractional order controller, the extension of derivative and integration order from integer to fractional order. Integer to fractional order. In the integer order PID controller, the order of the integrator or derivative controller is integer. But whereas in the fractional order controller, the order of the integrator or the derivator is non-integer. It gives more flexibility for the designer, thereby controlling the wide range of dynamics of a system. So the fractional order controller or fractional calculus, this concept is introduced in the 19th century itself, and there are so many definitions for the fractional calculus. Among that, I consider one definition. Okay. So fractional order PID controller, it involves an integrator of fractional order lambda and a differentiator of fractional order mu. Okay, it has the following transfer function like Kp plus Ki by s power lambda plus Kd into s power mu. For integer order PID controller, the transfer function is Kp plus Ki by s plus Kd into s. Lambda and mu are 1 in case of the integer order PID controller. But whereas for fractional order PID controller, lambda and mu are non-integer values. Okay. So from the classical controllers are particular cases of the FOPID controller. If lambda is equal to mu is equal to 1, it is a classical integer order PID controller. If both lambda is equal to mu is equal to 0, you will get a proportional controller. Lambda is equal to 0 and mu is equal to 1, proportional derivative controller is obtained. And for lambda is equal to 1 and mu is equal to 0, proportional integral controller is obtained. Okay, for non-integer values of the lambda and mu, you will get a fractional order PID controller. For non-integer values of the lambda and mu, you will get the fractional order PID controller. In our MATLAB, there is no tool to design the fractional order PID controller. Only in the MATLAB toolbox, okay, we have only PID controller. You can simulate the PID controller. But whereas to simulate the fractional order PID controller, you have to download the FormCon toolbox from the net. Okay, so some LSK is name. One introduced the FormCon toolbox. You can download from the internet or FormCon website. And you can install that FormCon toolbox in your MATLAB. Then only you can simulate the fractional order PID controller. Unless otherwise, you download or you have to add the FormCon toolbox to the MATLAB. Then only you can simulate the fractional order PID controller. Okay. So the main advantage of this fractional order PID controller is it has 2 more extra tuning knobs than the classical integer order PID controller. Okay, the use of fractional controller gives more flexibility for the design of a control system and gives better opportunity to adjust system dynamics. Where lambda is the integral order, mu is the differential order. In case of the integer order PID controller, Kp, Ki, Kd are the only parameters of the PID controller. But whereas for the fractional order PID controller, Kp, Ki, Kd and lambda comma mu can be evaluated. Lambda comma mu, these are the parameters. Okay, so the designer has the more flexibility to adjust the dynamics of system dynamics. Okay, so the parameters of the fraction order controller can be evaluated by applying some optimization techniques. Any of the optimization algorithms you say you can optimize the fraction order PID controller parameters. Okay. So first, optimization of FOPAD controller first needs the optimization goal, what you want to optimize. So in our problem, our objective is we want to eliminate the frequency deviation. We want to eliminate the frequency deviation and tie-line power exchanges near to the scheduled values by performing the suitable control action. That is the main objective or our optimization goal. Okay, for FOPAD controller, KP, K, KD and lambda comma mu are required to design according to the control objective. Okay, so to get our optimization goal, I want to tune the parameters KP, K, KD, lambda and mu. Okay, so to determine these parameters, okay, based on the experience like traditional controllers is not possible. And so fast and efficient way to optimize these parameters must be found. Here we used two optimization algorithms, particle swarm optimization and the cat swarm optimization. PSO, this particle swarm optimization, it attempts to mimic the natural process of group communication of individual knowledge. Sorry. Particle swarm optimization, it mimics the natural process of group communication of the individual knowledge, which occurs when swarms flock or migrate, forage, etc. in order to achieve some optimum properties such as configuration or location. Okay, while the birds migrate from one location to another to find a location, okay, they are going to communicate. The individual knowledge can be communicated for the group. So based on that, we use the particle swarm optimization. Next one is cat swarm optimization. It is a novel algorithm based on two major behaviors of the cats: seeking and tracing. Seeking mode and the tracing mode. The behavior of cats are modeled to solve the optimization problem employing a new learning rule. So to design the fraction order PID controller, first identify the fitness function. Identify the fitness function. For any optimization problem, you need to identify the objective function or the fitness function. If you identify the objective function, you can easily implement the optimization algorithm, any algorithm. Okay, the objective of the controller parameters optimization is to make the control error tend to 0. And there is small or overshoot and fast response. Here, to make the control error means to make the area control error 0. In order to obtain the satisfactory transition of the dynamic characteristics, integral square error has been used in this work as a performance index. Okay, I consider integral square error as the performance index for the parameters minimum objective function. So integral square error is equal to integral of 0 to t e of t whole square dt. Here e of t means I consider error signal is the area control error. So once you know the fitness function, then you can apply the optimization algorithm. Okay, so these are the steps for the this is the brief introduction for the particle swarm optimization. It employs swarm intelligence, which comes from cooperation and competition between the particles of a group to guide the optimization search with strong convergence, global optimization, and competition efficiency. Okay. In particle swarm optimization, the swarm is initialized with the population of random solution. Okay. First initialize the population. Population is nothing but random solution. Each particle in the swarm is different possible set of unknown parameters to be optimized. So in our problem, particle means Kp, Ki, Kd, lambda, comma mu is considered as a particle. Representing a point, this particle represents a point in the solution space. Each particle adjusts its flying experience and shares social information among particles. The main goal is to efficiently search the solution space by swarming the particle towards the best fitting solution encountered in previous iterations, with the intent of encountering the better solutions through the course of process and eventually converging on a single minimum error solution. Now I will explain the steps of the particle swarm optimization. First, randomly initialize the population, including the position and velocities in the feasible ranges. First, initialize the population. Let's say 10. Population is equal to 10 and 10 set of, I consider 10 set of Kp, Ki, Kd, lambda, mu. 10 particles. 10 particles. Each particle consists of 10 random Kp, Ki, Kd, lambda, comma mu in the feasible ranges. So in the presentation, I did not give the ranges, but in the published papers, I also mentioned the ranges of the Kp, Ki, Kd, lambda, comma mu. Now, so these are the equations for the velocity of each particle and the present position of each particle. So the position of a particle is equal to next position of a particle is equal to the present position plus with what velocity the particle is moving to get the optimum solution. For each individual of the population, calculate the fitness value or the performance criterion. Here our performance criterion is integral. I want to minimize the integral square error. So I consider the fitness function is equal to 1 by 1 plus integral square error. Why? Because I converted the minimization problem into a maximization problem. That's why I consider the fitness function is equal to 1 by 1 plus ISE. For each population, evaluate the fitness function. Now compare each individual's fitness function with the previous or personal best. The best evaluation among all the is denoted as global best. The best among all the personal best is denoted as the global best. Later, modify the member velocity of each individual according to the equation 1. For each iteration, modify the velocity and modify the member position of each individual according to the step 1. If the number of iterations reaches the maximum, then go to step 7. Otherwise, go to step 2. So for the new population, again evaluate the fitness function. Among that, try to determine the global best. So once you identify the global best, next try to generate the population or modify the position by adding the velocity. So these are the steps for the particle swarm optimization. By using this particle swarm optimization, I minimized the parameters of the proportional fractional order PID controller. So before going to the fractional order PID controller, I initially first designed the integer order PID controller using the PSO. So for the integer order PID controller, Kp, K, Kd are the parameters of the integer order PID controller, and B is the frequency biasing coefficient. in the 2-area or 3-area interconnected system, there is a frequency biasing quotient that is also considered as one of the parameter, okay, to reach the goal. Okay, in this design of the integer order PID controller, I consider the particle is equal to Kp, Ki, Kd, comma B. Okay, first initialize the population. Initialization of the population means you will get, let's say population is equal to 10. You will get 10 set of Kp, Ki, Kd and frequency biasing coefficients. For each set of for each solution, first evaluate the fitness function. Evaluate the fitness function. Okay. Now this fitness function is compared with the previous fitness function. Okay. So if the present performance criterion is better than the previous one, now store the present. Sorry. So once you got the local best, among the local best, try to identify the global best. Once you identify the global best, okay, the particle corresponding to the global best will be stored. For that particle, add velocity to reach the next position. Okay, so these are. So this is the table PSO based optimal parameters of IOPAD controller for area 1, area 2 and area 3. So these are the optimized parameters for the integer order PID controller. This integer order PID controller is applied in the 3-area interconnected power system. So these are the PSO based integer order PID controller. Okay, the settling time is 20 seconds. The settling time is 20 seconds for the PSO based IOPAD controller. Now coming to the fractional order PID controller, there are 2 more extra tuning knobs, lambda, comma mu. It gives more flexibility for the designer to adjust the dynamics of the system. So that is the main advantage of the fractional order PID controller over the integer order PID controller. Okay, in the integer order controller, only 3 parameters, Kp, Ki, Kd. But whereas in the fractional order PID controller, there are 2 more extra tuning knobs, lambda, comma mu. Where lambda is the order of the integrator and mu is the order of the differentiator, which is a non-integer value. Okay. So these are the optimal parameters for the fractional order PID controller for 1% step load variations. Okay, so there here also for the fractional order PID controller for PSO based, so you will get a settling time of at about 15 seconds. 15 seconds. Okay, I consider the load variation in area 2. Okay, so red color on the top graph, there is a frequency deviation in area 2, which is settled at 15 seconds. I also consider the wide range of parameter variation. This is plus 50% parameter variations, and this is for minus 50% parameter variations. Okay, for minus 50% parameter variations, the settling time is almost 10 seconds. The deviation in the frequency is settled. The deviation in frequency is settled at about 10 seconds. And the next optimization algorithm is cat swarm optimization. Okay, so it mainly on the behavior. The cat swarm optimization is implemented mainly based on the behavior of the cats. Mainly due to the behavior of the cats. So cats behavior generally ఎలా ఉంటుందంటే cats rest indolently most of time when they are awake. Okay, and move speedily when they are tracing some targets. Move speedily when they are tracing some targets. And cats also curious about all kinds of moving things. Cats also curious about all kinds of moving things. Okay, so these are the different hello. So this is about the behavior of the cats. Cats rest indolently most of time when they are awake, and they move speedily when they are tracing some targets. And cats are curious about all kinds of moving things. So based on this behavior, Chu and Pike proposed a new cat swarm optimization algorithm. Okay, so in the cat swarm optimization algorithm, so there are 4 parameters: m-dimensional position, velocities for each dimension, fitness value, seeking or tracing flag. Okay, like particle swarm optimization, there we are considering a particle. Here we are considering a cat. Okay, so there are two submodels in the cat swarm optimization. One is seeking mode, another one is the tracing mode. Okay, so the seeking mode is to model the situation of the cat. Seeking mode, it models the situation of the cat, which is resting, looking around, and seeking the next position to move to. ఓకే క్యాట్ సీకింగ్ మోడ్ లో ఉన్నప్పుడు ఏం చేస్తుందంటే ఇట్ సింప్లీ ఇన్ రెస్ట్ పొజిషన్ అండ్ లుకింగ్ అరౌండ్ అండ్ సీకింగ్ ద నెక్స్ట్ పొజిషన్ టు మూవ్ టు. అండ్ ట్రేసింగ్ మోడ్ ఈస్ ఫర్ మోడలింగ్ ద కేస్ ఆఫ్ క్యాట్, modeling the case of the cat is tracing some targets. When the cat is tracing some target, that can be modeled by using the tracing mode. Okay, the main parameters of the seeking mode are seeking memory pool. Seeking memory pool is the number of copies of each cat. All the copies of the cat are spread around their original cat based on the SRD range. Okay, so mainly there are two submodels. One is seeking mode and the another one is the tracing mode. Suppose if you consider 10 cats, some of the cats will be in seeking mode and some of the cats will be in tracing mode. Some of the cats, not all the cats are in seeking mode, or not all the cats are in tracing mode. Let's say our population is 10. Based on the mutuation ratio, based on the MR, based on the mutuation ratio, okay, the population is divided into two. That is cats which are in seeking mode and cats which are in tracing mode. Okay, so cats in seeking mode, they sit in rest position and they are looking around the looking around and seeking the next position to move to. Okay, so these are the important parameters in the seeking mode: seeking memory pool, SRD, seeking range of the selected dimensions, self position consideration, counts of dimension to change. Okay, so based on these parameters, okay, we can model the cat in the seeking mode. First one, seeking memory pool means number of copies of each cat. అంటే మన పాపులేషన్ లో లెట్స్ సే ఎంఆర్ అనేది 20% తీసుకున్నాం అనుకోండి. MR is equal to 20%, mutuation ratio 20% తీసుకున్నాం అనుకోండి. If you consider population is 10, okay, 2 cats will be in the tracing mode and 8 cats will be in the seeking mode. We are going to use some flag to identify which cat is in seeking mode and which cat is in tracing mode. Okay, we'll consider a cat and we'll check the flag. If the flag indicates the cat is in seeking mode, we need to consider these parameters. Okay, seeking memory pool is the number of copies of each cat. Number of copies of each cat. All the copies of a cat are spread around their original position. And in the search space, how many copies of cats you need to consider? Okay, that can be specified by seeking memory pool. Okay, all the copies of a cat are spread around their original cat based on the SRD range. SRD means seeking range of selected dimension. SRD specifies the distance between the original cat and its copies. మనకి సెర్చ్ స్పేస్ లో ఒరిజినల్ క్యాట్ కి అలాగే దానికి కాపీస్ గా తీసుకున్న క్యాట్స్ కి మధ్య ఉన్న డిస్టెన్స్ ని స్పెసిఫై చేసేదే SRD. నెక్స్ట్ వన్ సెల్ఫ్ పొజిషన్ కన్సిడరేషన్. ఇట్ ఈస్ ఏ బూలియన్ వేరియబుల్. ఈ బూలియన్ వేరియబుల్ 1 అని ఉందనుకోండి, వీఆర్ గోయింగ్ టు కన్సిడర్ ద సెల్ఫ్ పొజిషన్ ఆల్సో. Otherwise, we don't consider the self position. Okay, self position means where the cat is already standing. That is also considered. Okay, last one is counts of dimensions to change. CDC is the percentage of dimension to be changed to the total number of dimensions that describes the location of each cat. So there is a procedure for the seeking mode. There you can understand clearly what is a seeking mode and what is a tracing mode. If the CDC is counts of dimensions to change is 100%, the search directions will be like that. Okay, if CDC is equal to 100%, okay, the distribution of copies will be ball shaped. So the possible candidates to be searched around the cat are 8 vertices of a cube. But whereas if CDC is 66%, the distribution of copies will be 4 vertices of 3 plane surfaces. That have the original cat in the center. Blue color lo unnadi original cat. Blue color lo indicate chesindi original cat. If CDC is 100%, the possible candidates to be searched around the cat are 8 vertices of a cube. Okay, if CDC is set to 66%, the copies will be 4 vertices of 3 plane surfaces only. Okay, in general, a larger CDC value gives many possible candidates, generating lots of mutation. Now, so we already discussed the parameters of a seeking mode. So these are the parameters of a tracing mode. Tracing mode is nothing but, okay, it is the procedure which followed in the particle swarm optimization. So these are the parameter settings for the cat swarm optimization. Here I consider n, number of cats 10, number of cats in 10 consider chesanu. So SMP ante number of cats each cat makes in seeking mode. Okay, so MR at mutation ratio. MR 20% తీసుకున్నాం. 20% తీసుకుంటే ఏమవుతుందంటే నెంబర్ ఆఫ్ క్యాట్స్ 10 లో 2 are in tracing mode, 2 cats are in tracing mode, 8 cats will be in seeking mode. Okay, based on this parameter setting only, later I will explain the flowchart of the cat swarm optimization. Okay, first consider 10 cats. Among 10 cats, 2 cats are considered in tracing mode and 8 cats are considered in seeking mode. Once the cat is in seeking mode, for each cat, okay, seeking memory pool is 5. For each cat, seeking memory pool is 5, and for each cat, nearga I am going to consider 5 more cats. If SPC is 1, okay, I will consider the current position also. I will consider the previous slide explanation. SPC and self position consideration, where the cat is already standing. Okay, seeking memory pool lo మనం 5 cats ని కన్సిడర్ చేస్తాం కదా. 5 cats ని కన్సిడర్ చేసేటప్పుడు ఓకే ఆల్రెడీ కరెంట్ పొజిషన్ కన్సిడర్ చేసి ఇంకా 4 more cats ని కన్సిడర్ చేస్తాం. ఇప్పుడు ఇఫ్ SPC is equal to కనుక 1 అయితే కనుక, ఇఫ్ SPC is equal to 0 అయితే కనుక మనం కరెంట్ పొజిషన్ కన్సిడర్ చేయకుండా 5 డిఫరెంట్ క్యాట్స్ ని కన్సిడర్ చేస్తాం. Is this okay or not? Self position consideration, it is a Boolean variable. It is either 1 or 0. Self position consideration is a Boolean variable. It is either 1 or 0. If SPC is equal to 1 and the cat is already standing, then you consider some. If SPC is equal to 0, okay, you need to consider 5 different cats in the search space, which are in seeking mode. Next, SRD, selected range of dimensions, range of variation for each dimension in seeking mode. And మనం కన్సిడర్ చేసిన కాపీస్ నుంచి ఓకే ఎంత డిస్టెన్స్ ఒరిజినల్ క్యాట్ నుంచి కాపీస్ కి ఎంత డిస్టెన్స్ లో ఉండాలనేది ఈ ఎస్ఆర్డి అనేది మెన్షన్ చేస్తుంది. ప్రీవియస్ గా ఆల్రెడీ ఎక్స్ప్లెయిన్ చేశాను, చూడండి ఒకసారి. సెలెక్టెడ్ రేంజ్ ఆఫ్ డైమెన్షన్, SRD defines the distance between the original cat and its copies. Distance between the original cat and its copies can be specified by SRD. Okay, so R1 is a random variable for calculating the velocities, and ACC is the acceleration constant, which is taken as 2 from the references. So it is the flowchart of the cat swarm optimization. Create n cats. Here I am considering 10 cats. Initialize the position and velocities and the flag of every cat. Okay. Initial గా ప్రతి క్యాట్ కూడా ఎంత వెలాసిటీతో వెళ్తుంది, అలాగే దాని కరెంట్ పొజిషన్ ని we need to initialize, and also you need to initialize the flag for each cat. That flag indicates whether the cat is in seeking mode or in tracing mode. That flag means it is either 1 or 0. If you consider 1 for seeking mode and 0 for tracing mode, based on the flag, you can identify which cat is in seeking mode or which cat is in tracing mode. Once you identify whether the cat is in seeking mode or in tracing mode, so seeking mode, cat K is in the seeking mode. Next, for all the cats, evaluate the fitness function and keep the position of the cat which has the best fitness value. ఉన్నదాన్ని మనం will store. Later we can identify whether the cat is in the seeking mode or not. If the cat is in seeking mode, yes, follow the seeking mode process. If the cat is in tracing mode, follow the tracing mode process. Okay. If later repick number of cats and set them into tracing mode according to MR, and set the other into seeking mode. Okay, so this is the flow chart. Now I will explain the procedure for the seeking mode and the tracing mode. Okay, once you initialize the position, velocity and flag for every cat, okay, evaluate the fitness of all the cats and keep the position of the cat fitness function and keep the position of the cat which has the best fitness value. Okay, if the cat is in seeking mode, okay, among the 10 cats, only few are in tracing mode and only few are in seeking mode. Remaining are in seeking mode. Okay, that is depends on MR. In our problem, I consider MR is equal to 20%. Okay, that means for 10 cats, 2 cats are in tracing mode and 8 cats are in seeking mode. Okay, all the cats can be flagged. With the help of flags, we can specify 2 cats are in tracing mode and 8 cats are in seeking mode. Okay, so now these are the steps for the seeking mode. Just make J copies of the present position of a cat. Okay, where J is equal to seeking memory pool is equal to 5. ఇక్కడ మన ప్రాబ్లంలో సీకింగ్ మెమరీ పూల్ 5 కన్సిడర్ చేశాం కాబట్టి ప్రతి క్యాట్ కి కూడా 5 కాపీస్ ని తీసుకుంటుంది. సెట్ స్పేస్ లో ర్యాండమ్ గా 5 క్యాట్స్ ని కన్సిడర్ చేస్తాం. ఓకే, ఆ 5 క్యాట్స్ ఎంత డిస్టెన్స్ లో ఉంటాయి అంటే SRD, దట్ ఈస్ ప్లస్ ఆర్ మైనస్ 30%. ఓకే, అలాగే సీకింగ్ మెమరీ పూల్ 5 అని తీసుకున్నాము. ఇఫ్ SPC ఈజ్ ఈక్వల్ టు 1 అనుకోండి, ఓన్లీ ప్రజెంట్ కన్సిడర్ చేసిన పొజిషన్ తో పాటు 4 క్యాట్స్ ని మాత్రమే కన్సిడర్ చేస్తాము. SPC is equal to 0 అనుకోండి, then J is equal to SMP is equal to 5. If SPC is equal to 0 అయితే కనుక, if SPC is equal to 1 అయితే కనుక J is equal to SMP minus 1 is equal to 4 and retains the present position as one of the candidates. Now, for each copy, according to CDC, in our problem, I consider CDC is equal to 100%. Okay, randomly plus or minus SRD% the present values and replace the old ones. So this is the formula to make the copies. Okay, 1 plus or minus 0.3 random or with old position PK. Okay, next calculate the fitness value for all the candidate points. Calculate the fitness value for all the cats. Calculate the fitness value for all the cats. If fitness values are not exactly equal, calculate the selecting probability of each candidate point by using the equation 2. Otherwise, set all the selecting probability of each candidate point be 1. Okay, randomly pick the point to move to from the candidate's point and replace the position of cat. Okay, so these are the steps for the seeking mode of operation. Okay, so overall the steps are, okay, according to the seeking memory pool, we are going to prepare the copies of each cat and evaluate the fitness function for all the cats, determine the fitness value. So based on the fitness value, for best fitness one value in matram మనం store చేసుకుంటాము. And the termination criteria, if the number of iterations are over, okay, then terminate the program. Otherwise, go to the step 2. The step 2. Now coming to the tracing mode. So tracing mode, it is similar to the particle swarm optimization. Update the velocities for each dimension according to by using the equation 2 and 3. Okay, so in the particle swarm optimization also there are two equations. For the which indicates the position of the particle and velocity of the particle. Here also tracing mode lo position of the cat and velocity of the cat ne represent cheyadaniki equations are there. Okay, the procedure is same as the particle swarm optimization. Now, optimization of the fraction order PID controller by using the CSO. Okay. Here for integer order PID controller, only KP, Ki, KD, B are considered as a cat. For fractional order PID controller, KP, Ki, KD, lambda, mu, comma, B are considered as a cat. These are the parameter settings for CSO. These are the parameter settings for PSO. Number of cats 10, seeking memory pool 5. Selected range of dimension 30%, CDC 100%, okay, MR 20%, okay, R1 it is a random variable which is in between 0 to 1, acceleration coefficient is 2, okay, and the controller parameters and the corresponding value ranges. Okay, I also set the minimum and maximum ranges for the proportional controller, integral controller and the derivative controller. Fraction order integrator, fraction order differentiator. Okay, so these are the ranges for the controller parameters like KP, Ki, KD, lambda, mu and frequency biasing coefficient. B1, B2, B3 are the frequency biasing coefficients for the area 1, area 2 and area 3. And these are the ranges I consider in my optimization problem. Okay, so for the simulation of so these are the simulation results for the integer order PID controller. CSO based integer order PID controller. Okay, KP, Ki, KD and beta. In area 2 I consider the load variations. In area 2, I consider the load variation. So these are the optimal values for the integer order CSO based integer order PID controller. Okay, so for 1% step load variations, okay, so these are the frequency deviation. I consider again the load in the area 2. Okay, so it is the integer order PID controller. For integer order PID controller, okay, the settling time is almost 20 seconds. After 20 seconds, the frequency deviation is eliminated and tail-end power exchanges are brought to the near to the scheduled values after 20 seconds. Next, so these are the optimal parameters of the CSO based FOPID controller. Optimal parameters of the CSO based FOPID controller for area 1, area 2 and area 3. By using CAT form optimization, I determine the optimized parameters for the fraction order PID controller. So for 1% step load variation, okay, the settling time is at about 7 seconds. 7 seconds. Within 7 seconds after the load variation, the deviation in the frequency and tail-end power exchanges can be scheduled to the near to the scheduled values. There is deviation in the tail-end power and the deviation in the frequency. Okay. Which can be brought to the nominal values by using the CSO based FOPID controller within the 7 seconds. Okay, so these are the simulation results for the CSO based FOPID controller by considering the 50% parameter variations. 50% parameter variation, 6 seconds, 6 to 7 seconds. Okay, after applying the load perturbation within 7 seconds, the deviation in the frequency and tail-end power exchange can be brought to the nominal values. Okay, so these are the results for the considering minus 50% parameter variations. So completely. So this is about the comparative study of the settling time. Okay, I did not mention the peak overshoots. Why? Because peak overshoots almost any same ga vachinayi kabatti I only showed the settling time for 1% and 10% step load variations. Okay, so in the entire presentation we discussed the fuzzy integral controller. Fuzzy integral controller lo the deviation in the frequency and tail-end powers settling time was 20 seconds. 20 seconds for the fuzzy integral controller. For ANFIS controller, again within 50 seconds, frequency deviations and tail-end powers are brought to the nominal values. Again, next ANFIS for adaptive neuropathy inference system for plus 50% parameters and minus 50% parameters settling time ichchamu. Next one is PSO based integer order PID controller. Okay, our comparison is fractional order controller with the other controllers. Okay, other controllers means integer order controllers, intelligent controllers like fuzzy and ANFIS controllers. Okay, for PSO based IO PID controller, again 20 seconds we got, but whereas PSO based fractional order PID controller, we got 12 seconds only. We got 12 seconds only for the PSO based fractional order PID controller. So overall, next PSO based fractional order PID controller with plus 50% variation. Again, you will get 15 seconds as a settling time. For minus 15% parameter variations, you will get 12 seconds. Next, CSO based IO PID controller, CSO based integer order PID controller, no improvement. Why? Because it is the integer order PID controller. Okay, like integer order PID controller means it is a conventional PID controller. The setting time is 20 seconds. Finally, we implemented a CSO based FOPID controller whose settling time is 7 seconds. By considering parameter variations also, we improved the settling time, and within 7 seconds the deviation in the frequency is eliminated and brought to the nominal value. So from the above table, it can be concluded that the proposed ANFIS controller can handle the non-linearities and parametric uncertainties. At the same time, it is faster than the fuzzy integral controller. From the table, I can say that ANFIS controller, we are considering the parameter variations also. So I can say that ANFIS controller can handle the non-linearities and parameter uncertainties, and at the same time, it is faster than the fuzzy integral controller. Next conclusion is PSO based FOPAD controller is better than PSO based FOPAD controller is better than PSO based IOPAD controller and ANFIS controllers. PSO based FOPAD controller is better than PSO based IOPAD controller and ANFIS controller. And lastly, the performance of CSO based FOPAD controller is better than PSO based FOPAD controller and ANFIS controller for wide range of variations in the system parameters. So that's it about my presentation. Okay, so these are the references. Thank you. Okay. Thank you. Any queries? Sorry, a little bit fast because some technical problems are there.
No, sir. Everyone was appreciating the session. You can see the chat box, sir. They have posted excellent session and very informative session.
Okay, thank you, madam. Only my concentration is fractional order controller. Okay, తెలుసో లేదో తెలియదు. Fractional order controller అంటే present చాలా మోస్ట్ అడ్వాన్స్డ్ కంట్రోలర్ గా present యూజ్ చేస్తున్నారు మేడం రీసెర్చ్ లో.
Okay, sir. The platform is open for queries. If any participants are having queries, they can ask the questions, but they can post the questions through chat box. The feedback link for J2 session 1 has been posted. You just update the feedback. If anyone has questions, you can post the queries. Sir, just we'll wait for 2 minutes, sir. If
I will wait, no problem.
You may answer.
Thank you, sir. And now I would like to express our profound gratitude to our HOD, Dr. Sudhir Kumar sir, for his presence in this training program. And also I would like to thank the coordinators for their moral support and guidance. And I'm very happy to express vote of thanks for the resource person and faculty members who have made the workshop or training a grand success. Thank you, sir.
So thank you, sir. Sir, if any queries has been raised or shared, I will share to you through mail, sir.
Okay,
and I will share your mail ID, and if you allow us, if you share your PPT, we will share those things to the audience, sir.
Okay. Can I send the presentation?
Yes, sir. If
Okay,
you don't have any problem, you can share it.
I will send
at the last to the participants, sir, because they were asking through messages. So that's
Okay,
why
okay.
I
I will
have
send the
asked.
presentation. I will send the presentation.
Okay, sir. Thank you so much, sir. Thank you for your availability, sir. Thank you.
Thank you, ma'am. Thank you.
Thank you so much, sir. I request all the participants to join for the afternoon session at 2 p.m. sharply. So please fill the feedback link. It is mandatory. Thank you, sir. Thank you, Ravi, sir. Thank you so much.
Thank you, ma'am.
Thank you, sir. I request all the participants to submit the feedback link for day 2, session 1. And you may leave the meeting and please join for the afternoon session at 2 p.m. Thank you.